let's see what we got, and I'll try to work on that, work on the video. So it starts with the letter N. What is kind of this gassy sort of thing in outer space? A nebula, yep. So there are definitely different sizes of nebula, and there's different reasons that nebula occur. Honestly, for those of us who were out on the hill the other day, we saw it was in the constellation Lyra, and it was called a planetary nebula. It has nothing to do with planets. And I told you basically it's a retired star that has kind of schlepped off its material. That's gassy material, okay? And the cool thing about the way that stars like our sun are formed is they kind of recycle material that was left by other stars. Okay, so stars can live their lives, they kind of give their stuff back to the solar system for other stars to be formed from them. It was pretty exciting because actually our sun has spectral lines in it, according to it shows us it has iron in it, like the element iron. And our star did not make iron. That iron actually was made in another star that gave the material to this thing right here we're going to call the solar nebula. Okay, so solar nebula is basically early on what the stuff that ultimately formed our solar system. So as I've been up here, and you guys already knew this, okay, this is the sun. We need to talk about the formation of everything in our solar system. So the first unit of material was, of course, we got the sun, the planets, and then what do we have out kind of past the beginning about Pluto? What's it called? Start with letter K? Kuiper Belt, very good. And then what is this? The Oort cloud, yeah. So all of that stuff actually came from the solar nebula. So this is kind of showing at a glance what our solar system looks like. And this unit of material, this is a survey class. So survey means you get a little bit of everything. So we're going to talk in here a little bit about the formation of the planets. We're going to talk about the planets. Maybe I'll get some sound for video, and we'll watch some videos on the planets. And then, we're also going to, at the end of Unit 2, if you see the sheet I gave you, your marching orders for Unit 2, your Unit 2 homework. Remember, if you're like, well, now, Mrs. Snipes, how can I study for your stuff? How do I know where it is in my OpenStax books? Well, you can actually use your homework to kind of see. Right now we are hitting in Chapter 7 and Chapter 14, you would find material about the solar nebula, or the formation of our solar system. What was I saying? Oh yeah, so it's a survey class. If you have your homework handy, if you go ahead and scoot on to the end of Unit 2, we kind of segue from the planets to something more general called light and electromagnetic radiation. So what do you think? If there's a lot of questions like there are with regard to Part 4 in Unit 2, okay, you have to pick 5 of those. That just means it's a longer unit. Okay, so, and then we also end up talking about telescopes. So that's kind of what Unit 2 looks like. But so now we're talking about the formation of our solar system. At a glance, it kind of looks like this. So what direction does the Earth spin on its axis? Counterclockwise. And it also orbits the sun counterclockwise, okay? So just the way, you probably already kind of have a sense for the nebula, the solar nebula, before there were planets and before the sun turned on, that solar nebula had a little bit of rotation, right? And rotating objects have a special type of momentum called angular momentum. The other thing is we've been talking about, there'll be a test question over about these 4 rocky planets. Okay, and then what planet is after the asteroid belt? Jupiter, yeah. So Jupiter's here, and then we have our gas giants. And so as we talk about the formation of our system of planets, how did that work? Why did that happen? Okay. We need to, as we talk about how our solar system came to be what it is today, we need to apply the principles of what makes sense, the scientific method. So based upon observations and experimentations, we can kind of come up with how this happened. It's kind of neat that actually we can look into outer space with our telescopes and we can see other stars that are in the earlier stages of what we used to be in. Do you know what I mean? We can look at other systems. So things that we need to explain in our overall little story about the formation of our solar system include this whole counterclockwise bit. So you guys just a minute ago told me the Earth spins counterclockwise, looking down at the North Pole, and it orbits the sun counterclockwise. And all of the planets orbit the sun counterclockwise in the plane of the, starts with letter E? Ecliptic, yep, plane of the ecliptic, exactly. So how did that work? This says that planets spin, rotate on an axis like the Earth does once every 24 hours. And most of them are counterclockwise. We're going to see that starts with the letter V. What is the planet a little bit closer to the sun than the Earth? Venus, yeah. We're going to see that Venus actually, if you look down its north pole, it's rotating on its axis of rotation clockwise instead of counterclockwise. So, and most moons orbit counterclockwise and rotate on an axis counterclockwise.
So, I have a question.
Yeah.
When it says all planets orbit counterclockwise, and it says most planets also
Spin on the axis,
okay.
rotate, yeah. So this is see, yeah, this is rotate and this is orbit.
Okay.
Yep. So they all orbit in the plane of the ecliptic in the same direction. Okay. But we're going to see that Venus actually spins backwards. And we think that that Venus used to be normal, spinning counterclockwise on its axis, and the same phenomenon that actually bumped up against the Earth and gave us our moon and rotated our axis of rotation, Venus got even a more dose of that and basically walked it over. So it's almost spent 180. I think that's kind of neat. So one of the things in this class, I already mentioned the whole idea of we have kind of beginning with Mars inward, we have the rocky planets, then we have the asteroid belt, then we have these gas giants. Oh, that's on my little, that's okay. What I was going to do is draw a line right here. Just on this table, here we have a column with the inner, sometimes they're called inner or terrestrial rocky planets, and then we have the gas giants. What would you say about Pluto if you were to go ahead and say it was either a terrestrial or a gas giant? It's Pluto. It's more like a terrestrial. It's rocky. It's definitely not a gas giant. But I love Pluto, just to say. Okay. The other thing, and you may, over here, the Jovian planets, we'll be talking more about this, but let's see, who saw the rings of Saturn? Okay. Now, the thing about the rings of Saturn is that actually all Jovian planets have rings. And the rings are just, I might have mentioned it the other night, rings are just kind of rocky, icy things they're kind of like a skirt of material, okay, and so they reflect the sunlight. So Jupiter has rings, but they're not as cool. And actually the way it works is Saturn's rings should probably kind of diminish over time as the kind of material falls into the planet. All right. So I need to find just bear with me. I know you're in here somewhere. There it is. So I like this figure, but to me, you almost got to kind of do this with it. You kind of got to go, I'm going to put the number 1, oops, I'll put 1, 2, 3, kind of in that order. So to look at this figure, kind of think of this sort of thing is going to be ultimately, it's not a star yet. This is not a star. Okay, can you kind of see that gassy material around it? So that gassy material is that solar nebula that's going to ultimately, if this is our sun, go to form our sun and the planets. So it's a gravity thing and a time thing for basically the object at the center of that nebula to get most of the mass, and for this to go ahead and it'll be hot here, but the closer you get to the core of this, what ultimately became our sun, it's going to be hotter and hotter and hotter. Okay, so here in the middle is where it's very, very, very hot, and it's got a lot of pressure, and that's where you can have nuclear fusion go on. Okay. So probably the difference between 1 and 2 is that the star turned on. I'm kind of saying that because when the star turns on, did I talk about solar wind yet? I love solar wind. So the thing about here, the sun is actually, wind, you think of like, wind, like moving air. It literally has a positive pressure. It's not air because it's not like oxygen and nitrogen and that sort of thing, but it's actually electrons and stuff like that. So it has a positive pressure. Now, once the sun turned on, it basically kind of scooted all that matter away, or most of the matter away. Hopefully, a good thing for us is while it was forming, so also was the material kind of in grooves around it, kind of coming together, forming the planets. And then over here, it says stars return their material into space. If you want to think of this, this could be our planetary nebula, and you can see the star here, and you can kind of see the material kind of going out. So this could be like a star that's kind of ending its life. It looks like what we're going to call a low mass star because it didn't blow up. High mass stars blow up. Low mass stars, they just kind of go out like this. They give material back that can be recycled into new stars. So that's kind of, it's a beautiful thing. So this is an artist's rendition of maybe what things would have looked like in our plane of the ecliptic, which was going to become our plane of the ecliptic, early on before the sun turned on. Remember when the sun turned on, when it became hot enough in here to fuse hydrogen to form helium and release energy, then it got the solar wind, which kind of cleared the outer regions. So this would have been early on. This is called the solar nebula. So again, we've kind of got 1, 2, 3, 4, and actually these are labeled, which is good. Okay. So search the letter G. What does this look like? What do these arrows look like? Gravity. Yep. Yep. Gravity. And then as I understand it, there are some stars out there that don't have the spin to them. Some nebula that are going to form stars that don't have spin to them. In that case, actually, all the matter kind of goes into just the star. But since ours had some spin to it, okay, actually that's what allowed planets to form in a disk around the star. So here you can see gravity pulling in. Here you get a sense for kind of the rotation of matter around the object that's going to become the sun. Again, I wouldn't call this a sun yet. I'd call it we use the word prototype. I would call this a proto-sun. Okay, I can tell it's not a full-fledged sun because it's got stuff the solar wind hasn't picked off. And then here, and I kind of liken building planets to kind of making a snowball. So you can kind of see in the track, and again, it's a combination of a gravity thing and the object that is orbiting the proto-sun, okay, kind of clearing its track of stuff, gobbling up, making something larger. If you watch these videos, they'll kind of talk about early on, it was like vying for who's the biggest chunk, what's really going to be the planet in this particular orbit. Okay, and then here we're kind of, let's see, formation of protosun, solid particles, condensed, and this actually is still, the sun hasn't turned on, but you can kind of see the tracks of material that are coming together. I've heard a gravity thing, also electrostatic thing, to kind of this what I call the snowball process work. Now there's an important concept called the frost line. So what is between Mars and Jupiter? The asteroid belt. Yep. The asteroid belt kind of demarks what we call the frost line. And I think I might have mentioned this the other day. Where is it hotter? Do you think it's hotter over here, closer to the sun, or is it hotter over here? It's hotter closer to the sun. Right? And so because of that, actually, let's put it this way. Let's see. Oh, that'll work. The cooler you get, let's put it this way, the cooler you get, the more things are likely to go from a gas to a liquid or even a solid, okay, like ice cubes. Okay? The warmer you are, it's going to be a liquid or even a gas. Okay? So this is what we call the frost line. And so we kind of have these differences between our star system T. What do we call these types of planets? Terrestrial. Yep. And then did I say, what do we call these guys out here? There's a few names for them. Giants or gas giants. Sometimes the letter J, Jovian planets. Sometimes these guys are called Jovians. Okay. So here we have kind of this is all stuff that might have been in our nebula. Let's look at it that way. Okay. So I don't know if you guys can read these, but which one was most abundant in our nebula? Your choices are helium, hydrogen, hydrogen compounds, rock, or metals. Helium, yep. 98% of the nebula that made our solar system, okay, the solar nebula that made our solar system, was hydrogen. Where is most of the matter in our solar system? The sun, yep. So, yeah, the sun just definitely has the lion's share of the matter that makes up our solar system. So, yeah, so a lot of hydrogen here, helium. I already told you some iron on the sun that came from another star living its life and creating it. So, compounds, okay, hydrogen compounds. Do we got any water in here? That's a hydrogen compound. Yes, hydrogen compound, H2O. Other hydrogen compounds are methane, ammonia. Probably can't read this. Ammonia is NH3. Okay. So hydrogen gas on Earth. I know. Let's do it this way. Hydrogen gas on Earth. What do you think? Is it? How many people think it's a solid? How many people think it's a liquid? How many people think it's a gas? Okay, you were right. So look at it this way. Hydrogen gas. This will work. If I go out here, farther from the sun, nice and cold, okay, hydrogen gas actually can liquefy. Okay. So that's kind of what we're talking about here. Over here, closer to the sun, on the other side of the asteroid belt, no, it cannot. But what can solidify, liquefy or solidify are rock and metals. So let's see, what does K stand for? Kelvin, yes. So these are Kelvin temperatures. So this is saying, I guess this is, will not condense, but this is saying that your metals will go ahead and solidify at a warm temperature of 1,000 to 1,600 Kelvin. Okay, I know you're right. Rock a little bit takes a little bit cooler temperatures. Your ices takes even cooler temperatures, and yeah, these do not solidify or condense. So what does the word condense mean to you? What does condense mean? Like, when do you use the word condense? Yeah, vapors and waters. Maybe you say condense like if you're boiling something, you have water kind of condense on your lid. Yeah. And so condensing is something going from a gas to a liquid. Condensing. So what this is saying is the temperatures at which these things would go from a gas. Can you imagine rock that's vapor form? Well, there you go. Be a vapor, and it will turn into a liquid about 500 to 13,000 Kelvin. And here you need to get it less than 150 Kelvin in order for your water, these ices at low pressures, to go ahead and condense. So we have this frost line. And I already told you, yeah, it's already on here. So we have terrestrial planets and we have Jovian planets, and it kind of, the break is about the asteroid belt. That's it. That's it. So the next few slides kind of talk about what I call the snowball process. Okay, the snowball process is kind of what this planet is doing to go ahead and clear its orbit of material, gobble it up, make it part of its own. Remember, actually clearing its orbit is the criteria that Pluto failed. So from left to right, you kind of see time progressing, and over here, this would be kind of our nice little, neat little planets that formed. So a few terms here, because this class is a little bit about terms. Planetesimal, is that not a cute word or what? So planetesimal is a kind of like a piece of a planet. Okay, yep. Accretion is the snowball process. Sometimes those terms will make it to my test. Notice that it's not just a gravity thing, it's also electrostatic, and it's also actually simply running into each other to kind of get bigger and bigger. So this again is talking about the solar nebula. It's talking about condensation, something going from a vapor to a liquid and then maybe even cooling to a solid. Up here we see the planets. We kind of have the asteroid belt. We have the break here. And you can see these guys over here with these gas giants. They could actually condense out there, but over here it was too hot. So here it's hot and here it's cool. I mentioned that it's fun to be able to use telescopes to look outside of our solar system at what's happening to other stars. So this is actually a look at what's happening to a protoplanetary disk. What does proto mean? What do you think? What's a prototype mean? In the process, yep. In the process, yep. Protoplanetary disk. Do you know any planetary disks? Planets. Think planet and think disk. Think plane of the ecliptic. Saturn has a disk of material around it. But this would be a star with a disk of planets. So kind of think plane of the ecliptic. So this is a star, and this is the disk where planets are forming. So this is, I guess I shouldn't say star. I'll call it a protostar. And this is the disk where planets are forming. Anybody seen Orion lately? Well, okay, Orion, that's a trick question. Orion is actually more a fall constellation, which should be rising earlier and earlier. Okay. Nurseries, I know. Atlas of Planetary Nurseries. So these are all different little baby stars with little baby planets being born around them. This is kind of showing you what we've been talking about. See, this is a real photo. I think that's a photo. But this is looking kind of, instead of edge on, face on, where this is going to be the star, and you can kind of start to see this sort of, looks like a record player, doesn't it? If you guys know what record players look, or like records look like. It does look like a tree too. So those are going to hopefully kind of, starts with letter A, what do we call it when planets get bigger and bigger? Accretion, yep. Very good. So Barry mentioned Saturn, okay. Does Saturn have any moons? Does Jupiter have moons? Mm-hmm. So kind of along that way, they kind of formed a little bit similar to what I'm describing with planets forming around our sun, where these big gas giants out here, they got their set of moons, because they actually, as they were forming, they had spin to them, and they had kind of a disk to them too. Okay, so it was that's kind of, so this would represent, of course, it says the star or sun. Now here we have, this is a close-up of, this is a close-up of here. So we have kind of the solar nebula, the sun hasn't turned on. We have swirling matter kind of forming a disk around the sun to make the planets. And then this is Jupiter out here, and it's got stuff around it to make Jupiter or Saturn. It's got stuff around it to go ahead and make its moons. So kind of from top to bottom, that's how this one works. So up here we have the nebula. Okay, we have the nebula flattening out, and the reason it flattened out is because of its rotation. And then here you can kind of see some accretion going on, planetesimals forming. So based upon what I've been saying, how many people think, I'll put it in a formal question, is sun on yet? So right here. How many people think the sun is on yet? How many people think the sun is not on yet? Very good. because it doesn't have the solar wind that kind of cleared its, so here's where the sun turned on. Awesome. Yep, this talks about solar wind. That's the, in this class, you'll hear me go, and that's my solar wind. Yep, so I have to go over here and go. It's kind of nice because solar wind is really a positive pressure, and the solar wind is good in kind of keeping like little microorganisms from entering our solar system. And there are several spacecraft that are leaving the solar system, and two of them are the Viking 1 and the Viking 2 mission that I think launched in '76, or that's when they reached Mars. So anyway, they launched a long time ago. So the Viking is actually leaving what we call the influence of the solar wind. We ultimately call that bubble heliosphere. So anyway.
How come the gravitational pull doesn't keep the stuff there?
Like the solar wind, why does the solar wind escape? And
yeah, how does it get to push out the stuff out of it instead of the gravitational pull keeping it in?
Yeah, I hear what you're saying. It must have a certain amount. Well, the particles that make up the solar wind are actually kind of energy particles, and so they have a certain amount of speed with them, so they can actually get away from the influence of the mass.
Positive and negative particles.
Well, I would kind of think of it as, and it's a type of radiation that's kind of embedded in the solar wind, and I would think of it as it just has, we talk about momentum. Momentum is mass and velocity. Well, this has sufficient velocity to keep to get away. So, yeah, that's a good question. So kind of a bird's eye view of the solar system. I think I'm kind of wrapping up things here now. This is a good table of the planets. So, we could draw a break here. Okay, so these are in order. Yeah, this is okay. Right here. Okay, these guys, I'll put a T for terrestrial. I'll put a G for gas giants down here, and a break here. You guys told me Kuiper belt. I'll put a K there for Pluto and Eris. So there's kind of relative sizes. This here, so what does an AU stand for? Astronomical unit, yep. So it's not so surprising then. The Earth is 1 AU from the Sun. Venus is 0.723. Mercury is 0.387. So Jupiter is a little over 5 times the distance from the Sun than the Earth is. How about Neptune? There you go. This next column then, or these next set of columns, the first one's radius, mass, average density, radius, mass, average density. The density of water, by the way, is 1. So here, actually, which planet did I circle the density for? Saturn, yep. So the fact that Saturn is less dense than water, if you had a big enough bathtub, Saturn would float on top of water. So I think that's kind of fun. So the rocky planets are more dense than the gaseous planets. This is kind of fun. This one, the orbital period, that's how long it takes to orbit the sun, and this is how long it takes to spin on its axis. So did you guys have a question like this? Can you read up here which one spins on its axis the slowest? So that's this column right here, rotational period. Which one spins on its axis the slowest? What do you think? I'm thinking Venus. So it takes 243 days for it to complete one spin. Now those are Earth days. So that's craziness. It's true. When it goes to take one lap around we'll still pick on Venus, take one lap around the sun, it takes 225 days. So is that longer or shorter than Earth's year? Shorter. And one of the things we said that actually Kepler's third law said that if you go closer to the sun, what happens to how fast you're orbiting the sun? Go faster, yeah. not only does your circle get smaller, but literally you will travel faster. This last column then is the tilt. So what's Earth's tilt? What is the degrees? Yep. So find Earth, 23.5 degrees. That's the tilt. So what did I say about Venus? It got whacked. Okay. So what happens if you go a half a circle? What degrees is that? 180. Yep. So here we go. There's Venus's axis of rotation is tilted 177 degrees. So you're like 3 degrees with them being all the way back around. So that's kind of fun. Mars is tilted kind of similar to Earth. Oh, here's one. Uranus, what's its tilt? Yeah, 97. So what's that kind of like? On its side, yep. That's what Uranus is. This one is how cold is it there? So what do you think? It is as you kind of think. The closer it is to the sun, then the hotter the temperatures are. But we have a little bit of an anomaly here. Venus. So Venus is a little bit hotter than Mercury. And I'd ask you, I don't know if anybody knows, but actually it's what we call a runaway greenhouse effect. Venus is kind of a strange little planet in that when you look up at Venus through the telescope, you're not looking at, if you look at Mars, you're actually seeing the surface of Mars. But if you look at Venus, you're just seeing Venus's cloud tops. So it's got this crazy precipitation cycle where it's not water, it's actually sulfuric acid. We're going to see that Venus has only been successfully landed on by the Soviets, and that little thing sent back some awesome little pictures, but then it died.
Oh.
I know, that's kind of what spacecraft do. But anyway, Venus, and so it's got a runaway greenhouse effect, and so I mentioned that it rains sulfuric acid, and its clouds or its atmosphere is very thick with regard to carbon dioxide. Cool. Well, thanks for bearing with me. So, see how many of these you need to answer? 3. Thank you. So 3 of these will be due on Friday. And we'll see if we'll get some sound back.
I was just there.
I like to